Hi, welcome to Are This Lottery's Odds Really in Your Favor? Okay, so let's say there's a lottery where the odds of winning are 1 in 100 million. So that's 1 in 10 to the 8, so the probability of winning is 10 to the minus 8. Tickets cost $1 and the jackpot is $300 million. If more than one winning ticket is sold, the jackpot is split between the winners. It's getting close to the cutoff time to buy a ticket, and 200 million tickets have been sold. Are the odds in your favor for this lottery? Answering this question is going to involve the use of Poisson statistics. There is a Poisson statistics playlist on this channel, which you might want to watch first if you're not familiar with the Poisson distribution. Okay, so first, let's define what we mean when we say that the odds are or are not in your favor. If the odds are in your favor, that doesn't mean that you're probably going to win. For example, in this case, you're almost certainly going to lose. Instead, if the odds are in your favor, that means that if you played the lottery many, many times, so many more than 10 to the 8th times in this example, you would, on average, come out with more money than you started with. So for this example, let's imagine that you were to play this lottery 10 to the 9th times. That's 1 billion times. Your probability of winning is 1 in 10 to the 8, and another way of writing that is 10 to the minus 8. So on average, you would expect to win 10 to the 9 times 10 to the minus 8, which equals 10 times, and lose all of the rest of the times. Now, the cost of buying this many lottery tickets is 10 to the 9th dollars. That's $1 billion. Now, if a winning ticket always got the whole $300 million jackpot, then 10 wins would give a total of 10 times $300 million, which equals $3 billion, and the odds would definitely be in your favor. But the fact that the jackpot is split between winners complicates things. Instead of just looking at the odds of winning or losing, we have to take into account all of the possibilities. For example, first, there's the possibility that you lose. Second, there's the possibility that you win and have the only winning ticket. Third, you could win but have to split the jackpot with another winner. Also, you could win but have to split the jackpot with 2 other winners, and so on. Okay, so let's lay out some assumptions that we're going to make about this lottery. First, we're going to assume that the winning lottery numbers are randomly chosen. Second, we will also assume that the numbers on lottery tickets are randomly assigned, for example, by a computer's pseudo-random number generator. Also, many lotteries have multiple ways to win with prizes of different sizes. In such cases, we would have to include all the different ways you could win. For this lottery, we will assume that there is the jackpot and nothing else. Okay, so we said that the probability of winning was 10 to the minus 8. This means that the probability of losing is 1 minus 10 to the minus 8. Now, if you lose, you don't care how many other winners there are. But if you win, you need to split the jackpot with all of those other winners. So we need to find out the probability of there being n other winners, where n is 0, 1, 2, etc. If we have a large number of independent trials for a rare event to occur, then the probability that the event will occur n times is described by the Poisson distribution. Let's say that we have t trials, and the probability of the event occurring on any single trial is p. The average number of times the event will occur in t trials is pt. Let's define lambda equals pt. So for a Poisson process which occurs, on average, lambda times over a certain set of trials, the probability for it to occur n times in that set of trials is given by the Poisson distribution, shown here. In our example, the number of trials is the number of lottery tickets sold, and the rare event is a ticket having the winning numbers. So n is the number of winning tickets. Now, in our case, the probability of any given ticket winning is 10 to the minus 8, and the number of tickets sold is 2 times 10 to the 8. So on average, we expect 2 winners, and we set lambda equal to 2 in our Poisson distribution formula. So out of those 200 million other tickets sold, the probability that there would be 0 winners is 13.5%. The probability that there would be 1 winner is 27.1%. The probability that there would be 2 winners is also 27.1%, and so on. Okay, so now let's calculate to see if the odds are in your favor. Let's say that you play this lottery n times, where n is a very large number. Each ticket costs $1, so this is going to cost you n dollars. So the question is whether or not, on average, you'll end up with more than n dollars. Okay, so out of those n times that you play the lottery, you win 10 to the minus 8, n of them, and you lose 1 minus 10 to the minus 8, n of them. Of all the times that you lose, you get $0. So let's look at the 10 to the minus 8, n times that you win. Okay, so first, how many times will you win and get the whole jackpot? For this to happen, you must have a winning ticket and there must be no other winning tickets. To find out how often there are no other winning tickets, let's look at the n equals 0 entry in our table. So the probability for n to equal 0 is 13.5%. So of the 10 to the minus 8 n times that you win, you get the whole jackpot 13.5% of the time. So the number of times you get the entire jackpot is 10 to the minus 8 n times 0.135. That was 13.5%. When you win the entire jackpot, you get $300 million. So that's 3 times 10 to the $8. So from the times that you win the whole jackpot, you get a total of 10 to the minus 8 n times 0.135 times 3 times 10 to the $8, and that equals slightly more than 0.4 n dollars. Now let's look at the times when you split the jackpot with one other winner. So we look at the n equals 1 entry of our table, and we see that 27.1% of the time that you have a winning ticket, you share it with exactly one other winner. So the number of times that you get half the jackpot is 10 to the minus 8 n times 0.271. And half of the jackpot is 1.5 times 10 to the $8. So from the times that you share the jackpot with exactly one other person, you get 10 to the minus 8 n times 0.271 times 1.5 times 10 to the $8, and that's also slightly more than 0.4 n dollars. Next, for the times when you share the jackpot with 2 other winners, let's look at the n equals 2 entry from the table. So here the probability for n to equal 2 is 27.1%. So the number of times that you share the jackpot with 2 other people is 10 to the minus 8 n times 0.271. Now each of these times you get 1/3 of the jackpot, which is 10 to the $8. So the money you win from the times when you share the jackpot with 2 other winners is 10 to the minus 8 times 0.271 times 1 times 10 to the $8, and that equals 0.271 times n dollars. Okay, so we won't go through all of the cases all the way up to n equals 6, but we'll just give the results here. We'll ignore higher values of n, so the instances in which there's more than 6 other winners, as they contribute to less than 0.5% of the times that you win. Now, these numbers add up to 1.3 n dollars. Now, as the n lottery tickets cost n dollars, the average winnings of 1.3 n dollars are larger than the cost. So the odds are in fact in your favor, but not by much. If the jackpot had been $225 million instead of $300 million, the odds would have been against you. This shows that a naive calculation which fails to take into account splitting the jackpot with other winners can yield wrong conclusions. Okay, so there are also a few practical concerns that are probably worth mentioning. First, we didn't take into account that you'd probably have to pay taxes on the winnings. This will effectively decrease the size of the jackpot. Also, sometimes the advertised jackpot size for a lottery applies only if the winner is willing to take the winnings in installments over many years. If a winner wants all of their money up front, they may get a reduced jackpot. These considerations can change the conclusions above. And while we're at it, we should mention some refinements that could be made in the above calculation. First of all, we assumed that the numbers on the lottery tickets were assigned randomly. However, many lotteries let players choose the numbers they want to play. And so, well, people may not choose numbers randomly. For example, they may choose numbers based on their birthday, or avoid numbers they think are unlucky. These effects could make the number of winners no longer Poisson distributed. Now, this won't affect your chances of having a winning ticket, but it can affect how many people you have to share the jackpot with if you win. It should also be pointed out that if one wanted to seriously consider whether or not it was in one's best interest to play the lottery, there would be many other considerations to take into account. To illustrate, if you're making a special trip in your car to go buy a lottery ticket, you should include the cost of gasoline and wear and tear on your car in the calculation. And on a more depressing note, you might also want to include in the calculation the probability of being in a car accident on the way to or from buying a lottery ticket. Now, you might consider being in a car accident a highly improbable event that you're willing to ignore, but winning the jackpot is also a highly improbable event. Lastly, you might not assign the same value to a certain unit of money at all times. For example, if you have all of your expenses covered and no serious monetary concerns, spending $20 on lottery tickets may not be much of a sacrifice. But if you're having trouble paying your bills one month and that $20 makes the difference between having your electricity cut off or not, that $20 may have much more value to you than its face value would imply. So while $300 million has a face value, a factor of 1.5 times 10 to the 7th, larger than that of a $20 bill, depending on your circumstances, its value to you may be more or less than 1.5 times 10 to the 7 times the value $20 has to you. Okay, so hopefully we've demonstrated in this video that a naive calculation of lottery odds can be misleading. We've looked at the effect splitting the jackpot can have on your average winnings. This was also a good demonstration of Poisson statistics in everyday life. And lastly, we've pointed out that a more precise calculation should take into account many other effects as well.